Hi everyone, welcome back. In this particular video, we're going to start talking about a new functional group, alcohols. And in this first segment, we're going to start discussing the synthesis of alcohols. Now, these are syntheses of alcohols that we've previously learned. So this is going to be a quick refresher. And then we are going to transition into some new methods of synthesizing alcohols. Okay, so let's get started. So the very first synthesis of alcohols that we learned in organic chemistry is from alkyl halides. Okay, so alkyl halides can be converted into alcohols, and this is by using substitution reaction. And since we're talking about synthesis, the specific substitution reaction, which is more useful, is the SN2 reaction. So for example, if we have an alkyl halide, okay, if that is an alkyl halide, what we can do is we can react this alkyl halide with sodium hydroxide or some hydroxide source. So let's say sodium hydroxide. So when we react it with sodium hydroxide, that's a strong nucleophile. And if you do this reaction in a polar aprotic solvent, so for example, DMF, then we can do an SN2 reaction where this halide would be substituted by that hydroxide, and our product is going to be an alcohol. And since this is an SN2 reaction, I hope you recollect that this is a synchronous or a simultaneous process, concerted process. Okay, so the hydroxide attacks and the alkyl, the halide leaves. That's a good nucleophile. So our product here is going to be an alcohol. So we start from an alkyl halide, and our product is an alcohol. Now, the second set of reactions that we've previously seen are starting from alkenes. So alkenes can be converted into alcohols. And we've learned a few different ways of doing it. Okay, so from alkenes, the first strategy or the first reaction that we've learned is the hydration reaction. The hydration of alkenes, this uses dilute acid, typically sulfuric acid is what we use, or you could just show hydronium ion. Okay. Dilute sulfuric acid or hydronium ion. So if we have an alkene, then we react this with dilute sulfuric acid, or like I said, you could just write hydronium ions to show the presence of acid. When we do this, the product here is an alcohol. Okay, so we make the alcohol, and this alcohol that's formed, this is the more substituted alcohol. That's our product from this particular reaction. Another important thing that you want to remember about this reaction is that carbocation rearrangements are possible here. Okay, so carbocation intermediate is involved, so the rearrangement products could be are possible, and in some cases the rearrangement product could be the major product, because it is the more substituted carbocation that results in that product. Okay, now a reaction that allows us to make the more substituted alcohol without the possibility of rearrangements or by avoiding rearrangements is the oxymercuration demarcuration. This reaction is done in two steps. We start with the alkene, and you first do an oxymercuration. This uses mercuric acetate as the reagent. Now the hydroxyl group in the alcohol comes from the solvent that's used here, which is water. So if we use water as a solvent in this first step, we will get the alcohol, the hydroxyl group of the alcohol. That's the first step. You have to finish this off with a reduction using sodium borohydride. We are going to learn more about sodium borohydride and its use in making alcohols in a subsequent video. But when we do this, our product is identical to what we made using the hydration reaction. So more substituted alcohol. The advantage here is no rearrangements, because this reaction, the mechanism of this reaction does not involve a carbocation intermediate. So since we avoid a carbocation intermediate, we can make the more substituted alcohol without the possibility of rearrangements. So wherever the alkene is, the more substituted carbon would get the hydroxyl group. So those are two reactions that both give us the more substituted alcohol. There's a third possibility, or a third reaction starting from an alcohol, from an alkene that can be used. So starting from an alkene, we can do a hydroboration oxidation. Okay. This reaction is also done in two steps. So this is a follow-up from here. This reaction is also done in two steps. And starting from an alkene, we have to do the hydroboration step first. We can do this using a borane reagent like borane THF. So you could use BH3 THF, which is just the simplest borane. Or you could use some alkyl borane, so like R2BH instead. The reaction is usually done in THF as a solvent. Okay, so an alkyl borane can be used in this particular case. So either way, or either a borane reagent or like any borane reagent, as long as you have a borane hydrogen bond, that can be used here. And you follow this with an oxidation, which is using hydrogen peroxide under basic conditions. So there's sodium hydroxide. And when we do this reaction would give us a less substituted alcohol. So compare the regiochemistry of where the hydroxyl ends up with the hydration reaction or the oxymercuration demarcuration. So we get the less substituted alcohol. And where possible, you can talk about stereochemistry here, because this reaction results in a syn addition of the hydrogen and the hydroxyl group. Okay, a syn addition happens. Now I can show you a quick example here. What do we mean by the syn addition? Let me use a very simple example here. So if we use an alkene like that, in fact, let me use a disubstituted alkene. A monosubstituted alkene here. This is fine. Or in fact, this is a tri-substituted alkene. When I said di, I meant like two methyl groups. That is what I was referring to. But this is actually a tri-substituted alkene, a monosubstituted cyclohexene it is. And if we do the hydroboration oxidation reaction here, so the reagent is the same, what we have at the top here. If we use those reagents here, then the product that we get is going to be an alcohol at the less substituted carbon. That's where the hydroxyl group goes. And the hydrogen is added to the more substituted carbon. And notice how the stereochemistry of these two, the hydrogen and the hydroxyl, is syn with respect to each other. They're on the same phase. Now, this is one of the enantiomers. So you're going to make a racemic mixture here. So both enantiomers would be possible. Okay, so those are some reactions that we've learned previously for synthesizing alcohols. Now, these are just simple alcohols. Let's look at some other reactions that allow us to make diols. Okay, we can also talk about diols here. So once we've talked about all the reactions that we've sort of reviewed, all the reactions that we've previously covered, we'll start talking about the new reactions for synthesizing alcohols. And that would then introduce us to some of the new chemistry that we will be learning here. Okay. Now, synthesis of diols, which again, are basically compounds with two hydroxyl groups. And in this particular case, we're going to be talking about vicinal diols. That means the two hydroxyl groups are on adjacent carbon atoms. Okay, so the two hydroxyl groups are on adjacent carbon atoms. So the reactions that we learned for synthesizing diols are starting from alkenes. So starting from alkenes, we learned syn dihydroxylation. This is one of the reactions. And there are various reagents that can that can make this reaction happen. Okay, that can be used here. I'm going to use one of the more commonly used reagents, which is dilute potassium permanganate. This is cold and it's under basic conditions. So there's some base in there, like sodium hydroxide. So it's slightly basic. When we do this reaction, you will get syn dihydroxylation. You get two hydroxyl group, and they are both syn to each other. So we get a syn diol. Okay, like I said, this is one reagent that can be used for this reaction. The other reagent that gives the same reaction is osmium tetroxide. And osmium tetroxide is usually used with some peroxide. So you can put H2O2, let's say, as a simple example there. You use it with some peroxide. Osmium tetroxide would also give us the same diol. But it is a diol starting from an alkene. The second dihydroxylation, or the synthesis of diols that we encountered, was the anti-dihydroxylation. We will talk about this reaction a little bit more when we get to the ethers chapter, okay, epoxides. We'll talk about this a little bit more there. But in an anti-dihydroxylation, again, you start from an alkene, and I'm using the cyclic alkene as an example to maintain some consistency here. But if I start from that same alkene, and if I do an epoxidation on this alkene, for which I can use a peroxy acid, RCO3H, a familiar one that you may have encountered is MCPBA, metachloroperoxybenzoic acid. That's a very common peroxy acid that's used for doing this reaction. Okay, so peroxy acid, or it could be like peroxyacetic acid, could be something simpler. So when you do an epoxidation and follow it with an acidic hydrolysis, okay, the alkene is converted into what we can call the anti or diol. Okay, so we get the anti-diol as the product, or a trans diol. So these are, as I mentioned, this is just a review of the reactions that will give us alcohol, like an alcohol functional group in our product. So in subsequent videos, we're going to start talking about some new reactions, some new chemistry and reagents that are also helpful in converting another functional group, let's say, into alcohol. The product is always going to be an alcohol. So we'll continue with the theme, synthesis of alcohols. I hope this review was helpful. Please look forward to the upcoming video. Bye.